Um, so, okay, I didn't spend as much time editing this as I wanted to, but basically the problem is I didn't get quite as far as I wanted to. That's always, it seems to be a perennial problem, and the reason that happens is I've slowed things down a bit to try to make them as graspable as possible for everybody. That doesn't mean I achieved it, but so I'm the ultimate. I mean, I make the calls on, all right, we going to spend another day on this, or do we go hell bent toward the goal and keep moving? And I have a tendency to slow down a little bit. And then, of course, what happens at the end of the year is I realize we didn't quite get quite as far. I still think, I'm still of the opinion. Okay, you got a few less things, but hopefully you got them. Instead of, oh yeah, well, we covered 95 things. Did you understand them? No, but we covered them. You know, I guess I'd like to get a, yeah. I've exaggerated on both ends, but that's kind of it's the age-old dilemma of teaching in a school where they have a curriculum they want you to teach, and you want to be honest so that you teach what the curriculum said you were going to teach, and at the same time you want to be as you want to shape the curriculum for the people that it's really meant for. And so I always tussle with that. Yeah, you notice a couple of these things are just literally crossed out. I was going to, the ones I didn't cross out and just flat deleted were in the last section, the formula, this section. I had a whole bunch of trigonometry stuff here that went on to page 4, and I just wiped them out because, well, Xing them out, they were like this thick, and so you can't just X something out that's that, you know, they were formulas. So anyway, that doesn't mean I've done everything properly. Also, let me explain here. Behind each thing, there's either a book reference or an outline reference. And so when you see a Roman numeral 6 behind a term, that means that's Roman numeral 6 off the outline. So I wanted you to understand that coding, you know, that outline I gave you on Trig. Yeah. Or like here's another one. It says Roman numeral 1A. So outline Roman numeral 1 part A. So the idea here is if you can't remember, I see I don't have that behind the techniques. I probably should have added that, and I did not get to it. I do on the trig, I just don't on the algebra. Okay, 3 major sections. Terms, techniques, formulas. That's kind of the idea behind the 3 parts. Which one is the most important? Techniques. Because that's, if you're going to use a checklist, I would begin there. That doesn't mean the terms are unimportant. Because, I mean, just think about it. I'm going to use the terminology just like the book has been, just like we have been all semester. And I may ask you a question, and I may say, what is the complex conjugate of this? Okay, just so you know, on the exam, you cannot ask me, what is a complex conjugate? You got to know what it is, otherwise you won't be able to answer the question. So, will I ask you to define a complex conjugate? No, but I probably will just I will ask a question where you probably have to make use of, you have to know what it is. Yes? No, I don't do that. So, don't sit there and, you know, so do you get the idea with terms? Terms is not like, oh, I got to get the matching part. No, there's not going to be a matching part. I'm going to just have words like this in my test, and if you don't understand those words, it's going to totally freeze your ability. So you don't want that. So don't ignore these, but this is the real meat right here in techniques. Those are actually the instructional objectives that I had. You know, those are things I tried to teach, and you're supposed to know how to do. And so, zero in on that when you start your studying. And when you get stuck, of course, that's what we have Wednesday and Friday primarily are reserved for. So you can use this as a beginning point for questions for Wednesday and Friday. By the way, what I would love to have happen on Wednesday and Friday is that pretty much the whole class is taken over by your questions. In other words, I'd rather go where you want me to go. So don't expect me to come in and say, all right, here is the review. No, I'd rather go, all right, where do you want to dig in? And then somebody might say, yeah, could you go through common denominators from chapter 3? Or here's a problem I still have in my notebook from chapter 4, lesson 1, that I still don't understand. Could we go through that? Or what is this term on here? Slant asymptote, and how do you find it? And anything like that would be, well, that would be just very, very good for everybody. So don't, it's no time to be bashful. Let it out. And instead of me being upset with you for a question, just the opposite. I always appreciate questions so much. So you're assisting us, and you're assisting yourself. It's a good deal all the way around. Okay? So it's not too early to begin this, but I thought I wanted to get it to you a little earlier, but at least you got something to look at. I may have to make a few adjustments. It could be that I've included a couple things on there that I shouldn't have, and I may have a few things missing. It should be pretty accurate, though. Okay, now, before we go on to what I'm going to call Trig 9, do you have some questions from last time, Trig 8? I went through some identities with you. We repeated the reciprocal identities. I also repeated the three Pythagorean identities, and then I added two new, what we call ratio identities. Let's see, let's just quick state them. All right, the reciprocal identities. Who would like to give me one reciprocal identity? Yes.
Tan equals sine equals.
Okay, well that's a ratio identity.
No, but let me do that one.
That's a good one too.
Reciprocal. Cosecant equals 1 over sine.
Okay, there's one of the reciprocals. Cosecant is equal to 1 over the sine. Another one? Okay, they're on your review sheet, and we just wrote them yesterday. I guess I could write them again. It wouldn't hurt, but let me just show you where to find these. You're on your last page. Look in that last column up there. See that line going across? Well, there's some in there anyway. Yeah, see cotangent equals 1 over tangent. Cosecant equals 1 over sine. Secant equals 1 over cosine. Those three are called the reciprocal identities. I guess I can write them again. Let's do that. Actually, I wasn't even going to touch these today, but okay. Well, let's keep going with the people from the students. So there's the first one we got. What's another one? Another reciprocal identity.
Secant equals 1 over the cosine.
Okay, there's two of them, and the only other one that's called a reciprocal identity, Ashley? Thank you. By the way, those could all be written another way, couldn't they? Like what? Let me just ask. What's another way this one could be written? Instead of saying cosecant equals 1 over sine, you could say sine equals 1 over cosecant. So in other words, aren't they reciprocals of each other? And they could be written either way. Okay? Then, the Pythagorean identities. Who can give me one of those? One of the Pythagoreans. Christina? Yep. And another question? Or go ahead. You bet. Good. And we have a third one. Tori? Very good. Okay, then yesterday I added 2 ratio identities. You came out with one of them, but let's just get a volunteer to bring those up. Give me a ratio identity. Sam, can you give me one ratio identity? Yep. And really, if you got this one, the second one shouldn't be too hard, because isn't it just this one kind of flipped upside down? And what is that second one? I just want to get more people involved, not that I don't want to. Andy?
Cotangent equals cosine over sine.
You bet. Now, just so you know, usually in trig, I would give about 9 more identities. We just didn't have time to get to them, and that's some of the stuff I had to suck off of this chart before I handed it out to you. Okay, and here's the list. Okay, so it wasn't bad. I'm glad we did take the time and write those down and review them. And yesterday we spent some time proving some new identities that these were the key to proving, really, and your ability to do basic algebra. Because, for example, things like 1 minus cosine squared, I don't see that anywhere on this page that's up in front of you right now. Oh, yes, I do. Do you? Do you see 1 minus cosine squared as any part of any of those? Yeah, I see it as part of sine squared plus cosine squared equals 1 with a little bit of subtraction from both sides, right? If you subtract cosine squared from both sides, can you see it up there? That sine squared theta is equal to 1 minus. So these little, minor algebraic modifications, I don't know, I call them cousins of these identities. If you can see them popping out, then that really helps a lot when you prove identities. We just had a little bit of time with that. Now, unfortunately, we have only one day to view some of the graphs. But the good news is you really have a good groundwork behind you, because you know your charts. You know your behavior charts. I know you do, because I've been mercilessly quizzing you on them. Like a machine gun. And I did that intentionally, because honestly, that's the key stuff when you get into calculus. What stuff for trig are they going to want you to know? They're going to throw things like the sine of pi over 6 at you, and without too much trouble, I'm hoping you're going to go, pi over 6, well, that's 30, and the sine of 30 is 1 half. And without going to your calculator, you can come up with that. And that's what that was my intent. I was trying to get you to think like that, because that kind of thinking in calc is rewarded. And so, now, with that in mind, let's see if we can plot the sine. I want to do both on here. I want to do sine, and I want to do cosine on the same grid. Now, before we do anything, we got to get some angles set up here, huh? I'll probably have each, I see this thing got drifted a bit, so let me, oh, that's interesting. Okay. All right, I didn't have that stuff unified. I better do that right now. Okay, so now when I move those things, they'll move together. But what I'd like to do now is let's plot some points, okay? And our angles, I'm going to have each vertical notch, I'm going to think of that as 30 degrees, okay? So like 30, 60, 90, that works out well with 360, you know? But I don't want to use degrees, so there's 90. There's 180. There's 270. There's 360. Just barely have enough room to put negative pi over 2 right at the edge of the screen there. Okay. Now, and I wish I could have spent more time, as you noticed on that last quiz. I also like to expand the angles a little bit. Really, all a negative angle means is it's just a backwards way of going to the same places. And so on negative 30 degrees, it's just 330, isn't it? And so it really wouldn't have been a huge deal, but we didn't have time. Okay, what's the sign of 0? I want this to come from your minds now. Yeah, 0. What's the sign of pi over 6? One half, isn't it? So if this is 1, then 1/2 would be right here. Okay, what's the sign of 60? Pi over 3. Square root of 3 over 2, which actually is 0.866. I don't know, probably up about there. The sign of 90. Come on, this is supposed to be coming from you guys. You look like you're spectators. 1, right? It reaches its high point of 1. And now, doesn't the SIGN of the SINE still stay positive in the second quadrant? Yeah, because it's above. So it's going to be positive, but it's going to be slowly decreasing, right? And so when we go to this first angle here, to 120 degrees, or 2 pi over 3, now it's going to be back to the same number it was right here, the square root of 3 over 2. And then, isn't it at 60 going to be back to a half? I'm sorry, not 60, but what is this? 120, 150. It's going to be back to 1/2. And when it comes to 180 or pi, it's going to be back to 0. Okay, now, do you notice we've got our first, what? Sign, I guess you could call it a hump, roughly outlined. Please note, that is not a semicircle. It's a different shape. It's not a parabola. It looks a lot like a parabola too, but anyway, honestly, well, let's just keep going here a little bit further. In fact, a lot further. Okay, what happens when we do 30 degrees further and we're in the third quadrant? First of all, what happens to the SIGN of the SINE in quadrant 3? It becomes negative, right? And that's because we're going to dip below the line. And when we do 30 degrees below, we're going to be at negative 1/2. It should be about here. And when we do 60 degrees below that, down at 240, we should be at negative 0.866. And when we do 270 degrees, or 3 pi over 2, we should be at negative 1. And then we move to the fourth quadrant. In the fourth quadrant, it stays negative, but it's starting to go up. Then we go back to what? At the 30-degree angle here, that's going to be what? Let me get my bearings here. 270 plus 30, 300 degrees. We're going to be at negative square root of 3 over 2 again. And then at 330, we're going to be at negative 1/2. And at 360, we're going to be at 0. And the whole process starts all over again. If we went to negative 30 degrees, we would see that that too would be negative 1/2. 60 degrees, negative 8.66. 90 degrees. And so this curve just continues forever. And if we try, and this is what I'm really bad at, but I'm going to give it a shot anyway. And we have at least one cycle, a little bit more than one cycle. Actually, it's called one period of a sine curve. That is, how long does it take before it starts over again? In the case of the sine curve, it takes 360 degrees. And so, you know, if I had room here, I would keep going, and what? This thing would just be pasted right on here. And it just goes on forever this way, goes on forever this way. This fits so many things in creation. It's hard to believe. What you're listening to me on the sine waves right now, because every sound has to travel this way. Light waves, you're seeing class because of this, because light waves follow that. Electromagnetic waves, you wouldn't listen to radios or any electronics without this. This is a huge, huge thing. Okay. Now, on the same grid, I'm going to do the cosine. Now, as you know, the cosine is not the same critter. I'm going to change to blue here. Cosine of 0 is what? 1, right? Okay. And what's the cosine of 30 degrees? Square root of 3 over 2. 0.866. What's the cosine of, you know, I don't have 45 up here, but what's the cosine of 45? It's exactly the same as the sine of 45, isn't it? So here's the, what? The crossing point that's on both curves. I never did it on the sine curve. But if you look on your charts, isn't the sine of 45 exactly the same as the cosine? So it's the one place they cross. Okay, now back to 60 degrees. Cosine of 60 is 1/2. Cosine of 90, 0. Okay, cosine of 120, and already we're into the negatives for the cosines, right? Cosine starts getting negative in the second quadrant. Cosine of, this would be, I got to think here, 90, 120. So this is the cosine of a 60-degree angle. Cosine of 60 is 1/2. Because we're in the second quadrant, it's negative. Okay, then we're at 150 degrees. Cosine of 150 is a 30-degree angle. The cosine of 30 is the square root of 3 over 2, negative 0.866. Cosine of 180 degrees is negative 1. Okay, then when we go past that by 30 degrees, now we're into the third quadrant. What happens, first of all, to the SIGN of the cosine in the third quadrant? Still negative. But it's going to be increasing now. So now if we go to 210, 210 is a 30-degree angle, negative 0.866. Now we go 60 degrees past, we're at 240. 240 is just a 60-degree angle. Cosine of 60 is negative 1/2. Back up here, we're at 0. At 270, right? Cosine has collapsed. Okay, when we go into the fourth quadrant, 300 degrees. That's a 60-degree angle from the x-axis. The cosine of 60 is the same as the sine of 30, which is 1/2. But we're back to the positives. 270 plus 60. 330 degrees, or a 30-degree angle, 0.866. And 360 degrees, we're back up to 1. Just backing this up a little bit, in the negative range would look like this. Okay, and now we'll make a shot at this. Seems like if I take these smaller swipes, I don't do too bad. So in the blue, we have a little bit more than one period of a cosine curve. And you notice the cosine curve is exactly congruent to a sine curve. It just retarded by 90 degrees. So in a way, no rip on anyone whose last name is cosine, but the cosines do appear to be retarded. And that's not a bad way to remember. I don't mean that as any kind of a cut, because I'm sure I'm going to cut down a trig function. But anyway, it's not a bad way to remember it. It's just 90 degrees behind. Otherwise, it does everything exactly the same, doesn't it? Okay. And so, not too surprising. Now, you probably knew that, because when you looked at your sine and cosine lines on your chart, you noticed they had all the same numbers, didn't they? They had all these 1 over the square root of 2, square root of 3 over 2, 1/2. Over and over and over again with different signs. The numbers were the same, they just were in a slightly different place. And you know what? I could have even taught you to do your chart this way. Learn how to do the sine chart well, and then just wait till 90 degrees later to copy all the stuff in the sine line. And if you look, that would actually work. I suppose I could have taught it to you that way, but then I don't think I would have been teaching you enough about cosine. And I might have taught you a negative attitude about cosine. You know, we shouldn't. I suppose instead of calling it the retarded function, maybe I should call it the special function. Right? Isn't that I guess that's more modern. Special ed. This is the special trig function. Okay. Now, let's go on and do a tangent. Okay, so any questions here? Now, please note that both these curves, if I had wide enough screen, would go on forever. There's just no end. How many times can you go around a circle? You can keep going as long as you want. And you can go around in a positive direction, clockwise, and keep going further to the right, or you can go around counterclockwise, head that way forever. Okay. Now let's take a look at the tangent. This is a different creature. So we're going to kind of start from scratch here. Get an x-axis cut across here. And I don't know, let's just say this is our x-axis. Now, as far as where I'm going to put my angles this time, I guess I'm going to go with 30, 60, 90 again in a similar way. So this is my pi over 2, 90. So that's 3 more. That would be 180. 370. And then way on the end here would be the 2 pi. And we could go backwards. to, let's say, negative pi over 2. So I always like to have a little bit of the negative side in there, so you at least get a picture of what happens when it goes to the left. All right, now, something totally different about the tangent, and you know it because of your charts. The chart I kept having you fill out, because the tangent was the first time we ever had to put a UND in. Now, how does a UND translate to a graph? UND means, whoa, I can't do it. A vertical asymptote. Yes. It means I can't cross that line. And it's a vertical asymptote. So I should pull a dashed line up here. And now you tell me, where are the UNDs for tangent? Pi over 2. So let's get one in right here. That means we know our graph can't cross there. Where's the next one? Yep, at every one of those y-axis places, right? And if we went backwards, negative pi over 2. Okay? Now, the only thing that throws it off is this is not an asymptote right here, okay? This is my good old y-axis here, and notice it's the only one. Okay, so you might look at that and go, that doesn't look quite right. But if you look, my dashed lines are all equally spaced, aren't they? Okay, now tell me what you know. The tangent of 0 degrees is? You bet. What's the tangent of 30 degrees? Yeah, now this one I'm going to have to look up. But let's do 60. This is the square root of 3, which is 1.703. Why do I remember that? I don't know. So let's have this be 1 right here. So 60 degrees, we're up about here. Tangent of 45 degrees is exactly 1. Somebody quick do on their, does anybody have a calculator? Could you do 1 over the square root of 3 for me? Thanks. 0.57, so about here. Okay, so you see what's going on. Now, what happens when we get, like, give me, let's see what we got here, 30, 45, 60. So halfway between 60 and 90 would be 75 degrees. Could somebody do the tangent of 75 degrees? Yeah, you got to make sure you're in degree mode. 1, 2, 3.73. Does that sound right? Okay, so do you guys see what's going on up here? Not surprisingly, it seems to be approaching the asymptote. Now, you already know that's what graphs do when they get close to asymptotes very frequently, don't they? And then what's going to happen over here on the negative side? Well, it's going to mirror image everything over here, except it's going to be negative in the fourth quadrant. Negative 60 is going to be negative 0.577. Negative 60 is going to be, negative 45 is going to be negative 1. Then we're going to be up about here. And at halfway between, we're going to be about here. And so what do you get? You get a branch that looks like this. I'm sorry that's so crude, but it almost looks like cube. Doesn't it almost look like x cubed? It's got some similar patterns to it, but it's not. It's its own thing. And so there's one branch. Then what happens is we get past 90 degrees. It vanishes at 90. And where does it reappear? At negative infinity again. And the process starts over. Now, I don't know if I'm going to be able to do this, but if I'd made this into one curve, it wouldn't have been so bad. Wow. I'm probably going to get too much for this, but we'll try it anyway. No, didn't want to do that. Yeah, I can't quite move that one over. Try it again. So you get the idea. This tangent curve keeps repeating, and it keeps vanishing every time it gets to what? The y-axis. 90 to 70 is where those UNDs appear and where those asymptotes appear, and that's our Mr. Tangent. So let me just write that on the top. So this is y equals tangent theta. Can't pick the pen up. So this is actually the theta axis here. This is the y-axis, technically. And back on our sine cosine graph, this is again the theta axis. This is the y-axis. Oh no, I guess here I used x. Well, we can remedy that. Okay, now, boy, I wish I had more time. There's so many cool things you can do. First of all, I wanted to show you the reciprocal functions. It's really beautiful how the reciprocal functions relate to the function of the reciprocal of. And I'm going to at least show you one of them, okay? So let's do this. And again, your calculator help would be appreciated. Let's take the sine function, the black curve on this graph, and let's try to plot at least a little bit of its reciprocal. The reciprocal of the sine, as you well know, is the cosecant. Okay, now, one thing unique about the cosecant is it has UNDs. You know, every time you try to take the reciprocal of 0, you're going to have a problem. And where is the sign 0? All you got to do is look. Right here, right here, right here. So at those places, we're going to have asymptotes, aren't we? So I'm going to throw some on here. So I should maybe make that a little bit longer. I'm not manipulating very well today. There we go. Okay, so there's one. There should be one over here. There should be one over here. Okay. And there's one place where the reciprocal is equal to the thing it's reciprocal of. What's the only number that's equal to its reciprocal? That's right, 1. So right here, so now where is the sign 1? Right here. And also, we should have said -1 too, right? Right here. Oh, you could just barely see it, but over here in the corner. Okay, well, I'm running out of time, but what's going to happen here is you're going to get... That's supposed to touch. And then this comes up from down here. And you see how the reciprocal functions just kiss? And then they part. They kiss at one point, and then, but they're, notice every place there's a high point on the sine curve, there is a low point on the cosine, and I never showed you that because we didn't study we didn't have time to study the behavior charts of the reciprocal functions, but every time there's a, increasing on the sine curve, guess what happens on its reciprocal function? It's a decrease. So it's just a perfect complement. Anyway, these things actually turn out to be rather beautiful. Another cool thing you could do is you can add trig functions together. You could have a function that looks like this: y equals sine theta plus cosine theta. And you can add them together, and they add real beautifully together. And in fact, as you add different trig curves together, what you get are kind of the curves of life. For example, if you have ever looked at a readout in a hospital of a cardiogram, okay, what you're going to get is not perfect, but you're going to get something like this. Of course, it's not perfect because our hearts aren't perfect, and different things happen. And sometimes you cough, and that throws things off, and stuff like that. But basically, the rhythm of life. I mean, I can't tell you how many things fit this rhythm. That would be that's another whole presentation I'd love to give to you, but we're out of time. So at least I gave you a little intro to the graphing of trig functions. And so, start taking into your review. I will see you tomorrow. Question? I would expect you to, how far would I expect you to go?